what's the nth root of the complex z? N is a positive integer. And later we're going to find out the square root of I. So first of all, I'm going to let nth root of z equal to w. W is some complex number and raised to the power of n on both sides. We have z equal to w to the power of n. And if we rewrite z into a trigonometric form into capital R times cosine alpha plus I sine alpha, where capital R is the modulus of the complex number or the length of the vector if you treat this complex number as a vector. And alpha is the angle of the complex number. And if we rewrite w into little r times cosine beta plus I times sine beta. Likewise, little r is the modulus of w and beta is the angle of w. And so this relation tells us that this equal to this to the power of n, right? So r equals r cosine alpha plus I sine alpha is in fact equal to the this to the power of n according to the de Moivre's rule, right? Our new complex number, the length should be little r raised to the power of n. And our new complex number, our angle should be the original angle times n. So cosine n beta plus I sine n beta, right? According to de Moivre's rule. So which means correspondingly little r should equal to, capital R should equal to little r to the power of n. And of course we assume that both capital R and little r are non-zero, are both strictly positive, because if they were zero then it'll be just trivial, right? So first of all, so which means little r is the nth root of capital R, right? And according to the angles should be equal to each other correspondingly as well, right? So n beta is equal to alpha plus 2k pi, right? Because cosine and sine are periodic functions, period of 2 pi, right? And k cannot be just any positive, it cannot be just any integer, but k actually is limited into some restrictions. I'll show. Beta is equal to n alpha plus 2k pi. K goes from 0, 1, 2, all the way up to n minus 1. The reason is because if k was equal to n, then that will be 2n pi divided by n will become 2 pi, right? It'll again become some angle plus 2 pi. Then it'll have exactly the same consequence in terms of cosine and sine, right? So it'll be just repetitive again, so meaningless. So this is our restriction, right? But if k was equal to -1, -2, something like that, then it'll be equal to exactly the for example, when k is equal to n minus 1, right? Similar, same thing. So we just ignore the negative cases because it'll be exactly the same. So we only restrict it into 0, 1, 2, all the way up to n minus 1. So we have exactly n different roots that all satisfy that relation, right? So this is our result. So then I'm going to find out what's the difference between consecutive roots, right? So for example, when k was equal to 1, k is equal to 2, what's their difference, right? So beta when k equal to 1, beta when equal to 2, so they just minus each other, so alpha over n cancel out. So 2 pi over n, then I have 4 pi over n. What's their difference? 2 pi over n. So each consecutive roots, their angles differ by. So beta sub k minus 1 beta sub k is equal to exactly 2 pi over n. So 2 pi is the angle of a full circle, right? We just divide the full circle into n equal parts, which means these n different roots happen to be the vertices of the inscribed regular n-sided polygon inside a circle, right? Well, what's the radius of the circle? The radius of the circle is little r, right? That's our geometric meaning. So we have, for example, this right, this origin, real part, imaginary part. This is our circle. So, for example, our first root, when k is equal to 0, it's going to be equal to alpha over n. That's our angle, right? For example, the angle is somewhere here, right? This alpha over n. This is our first root. And our second root may be somewhere here, right? Our third root somewhere here, fourth root somewhere here, fifth root somewhere here, sixth root somewhere here, seventh root somewhere here, and the eighth root somewhere here, right? So we have a inscribed regular and here, right? So this connected to that, this vertex, that vertex, this vertex, that vertex, this vertex, that vertex, right? So inscribed, equal-sided. So this angle, right? Here's another angle, right? This angle is equal to this angle, equal to this angle, equal to 2 pi over n, all equal to each other. And the original first angle is alpha over n, may be different from this one, right? Maybe same, maybe different. But this is the geometric meaning. And if we just take any root, for example, take this root, raise it to the power of n, eventually it'll reach our original complex number z. Z, the angle may be somewhere here, right? The length may be up here if we assume r, little r is larger than 1, all right? Capital R is also larger than 1. Maybe z is somewhere here. Take, for example, this root, raise it to the power n, that is times itself repetitively, meaning its angle will increase repetitively, right, incrementally. Each time times itself, the angle will increase by, for example, this angle of this root is this angle, right? Each time it times itself, it'll just increase by this much, this angle, right? Times itself twice, maybe it'll end up somewhere here, right? Length is also expanded, right? Length squared somewhere here. Times itself again, angle increased up to here, and length also expanded here. And repetitively until times itself for n times. And angle keep increasing, length keep expanding, right? Until it reach here, the z, where the z is, right? Length of z and angle of z, somewhere here. Likewise, if you take any root at all, take, for example, this is also a root, right? Same thing, right? Times itself repetitively n times, angle keeps increasing, right? Keeps increasing over and over, right? So all depending on the root, specific position of the root. Maybe if the root is here, it doesn't necessarily circulate just one circle. Maybe it'll circulate several circles until it reach where z is, right? If the root has a very large angle somewhere here, right, it will circle several times. If the little r is less than 1, larger than 0, right? So that means if the larger capital R is less than 1, larger than 0, then maybe if we if we multiply the root itself repetitively, then the length will shortened. Right? The length will be shortened. Right? The angle will keep increasing. Right? Length may be shortened. Maybe z is somewhere here, right? Very short. Angle is this angle, right? If we take the root, right, times itself repetitively, right? Right? Angle keeps increasing, right? Length keeps shortening. Eventually, it'll reach where z is, right? Likewise, if you take the root somewhere here, right, this root, then it'll be circled several times, right? Several circles, right? One circle, two circles, several circles, right? Eventually end up where z is, right? Length is shortened, right? And now what's the square root of I? So, square root of I, right? This time the, what's n? Nth root, n is 2, right? So what's the length? What's the length of the original I? Length is 1, right? So for example, I is the original complex number written into trigonometric form, right? Capital R, capital L, R is just 1, right? Length is just obviously 1 times cosine. What's the angle of this complex number, right? No real parts, only imaginary part. Obviously, an angle is pi over 2 plus I sine pi over 2, right? So, according to our formula, right, the little r is the nth root of capital R. Capital R is 1. The second root, square root of 1 is just 1, right? 1 times cosine, what's the angle, right? Angle beta is equal to this when n equals to 2, right? Alpha is pi over 2. And the k goes from 0, 1, up to 1 only, because n is equal to 2. 2 minus 1 is 1, only up to 1. So only two possibilities, 0 and 1. So half of alpha, that is half pi plus 2k pi, 2k plus I sine of half pi plus 2k pi. So in this case, square root of I is really equal to, just omitting 1 here, yes, cosine of, when k is equal to 0, that is equal to pi over 4. Pi over 4, right? So that is equal to, alternatively, k is equal to 1, right? Half pi plus 2 pi, that's 5 pi over 2, 5 pi over 4. Plus I sine 5 pi over 4, right? So two solutions, right? Cosine pi over 4, first quadrant, right? It's 45 degrees, easily half of square root of 2. Plus half of square root of 2 times I. And this is equal to the 5 pi over 4. I believe it's in the third quadrant, right? Because 4 pi over 4 pi is here. And 5 pi, that's here. This 45 degree, or this 225 degrees, right? Somewhere here. So that's negative half of square root of 2 minus, because both cosine and sine are both negative inside the third quadrant, minus half square root of 2 times I. Right? We can later double check. I'm not going to double check. It's easily verifiable that if we raise it to the power of 2, they both result in just I. So really, these are the only two solutions. Two unique solutions for square root of I. Right. So it turns out that we don't have to invent any other, which means square root of I is still in the complex number field. Right? We don't need to invent any other number system to solve for I. Solve for square root of I. And I will be using this result in future videos.